Hi again and welcome to Real Analysis, Calculus 6, Limits and Continuity. So, what is the definition of a limit, or what is a limit? The limit of a function describes the behavior of the function as the variable approaches a particular point. As the variable x of f of x approaches a particular point, what happens to the function itself? Limits often do not describe a specific discrete value of the function, but rather a threshold that the function approaches, okay? So, or a value that the function approaches as the variable approaches its own value. So as the variable x approaches a specific value, the function also approaches a specific level or height. For more definition, or epsilon-delta definition, let f be within a domain that is included in R, which is the space of real numbers, and let a be a limit point of the domain D. We say that limit f of x as x approaches a is equal to L if and only if for every epsilon greater than 0 there exists a number delta greater than 0, both of them infinitesimal numbers, such that for all x within D, you have x minus a is between 0 and delta. So the distance, when the distance of between x and a approaches a very small value, which is delta, then f of x minus L becomes less than epsilon. So x minus a, an absolute value, which is only the distance, a scalar distance. When it becomes less than delta, then f of x minus L, which is the limit, an absolute value becomes less than epsilon, or in other words, as x approaches a, in a sort that the gap between them becomes very small, then f of x approaches L, the limit, the height, the value, such as also the gap between them, the distance becomes very, very small, close to epsilon. Graphically speaking, okay, if we look at x minus a less than delta, so what does it mean? You have when the distance between x and a becomes very small, less than delta, which is a very small number, very close to 0 by the way, then the distance between f of x and L, the limit, okay, becomes close to epsilon. Here is the graphical representation. So as x approaches a such that the distance between x and a, the point, the value for which we are evaluating the limit, becomes very small and close to delta. At the same time, f of x approaches the limit L, which is if the function is defined at that point, you can say that f of a is equal to L, such that the distance between f of x and L becomes very small and close to epsilon. Delta and epsilon are very small numbers, close to 0. Example, let f of x be equal to 3x plus 2. Use the epsilon delta method to prove that limit f of x as x approaches 1 is equal to 5. Okay, so we know the limit is equal to 5. Actually, f of 1 is 5. If you replace simply x by 1, f of 1 becomes 3 plus 2, 5. But we need to prove that this is the case using an analytical method. So we know that the formula or the law of the limit is, let there be an epsilon number, which is very close to 0, greater than 0, a delta number greater than 0, but very small and close to 0. You have f of x minus L, f of x minus the limit is less than epsilon for each or every x satisfying x minus x0, which is, by the way, 1, is less than delta. So whenever x approaches x0 such that the gap between them is less than delta, which is a very small number, then as well f of x approaches L such that, which is the limit, which is 5, such that the distance between f of x and L becomes less than epsilon. All right, now x minus 1 is less than delta. Okay, how to evaluate that? We need to get from here to here. So you simply start by the simple premise that x minus x0 should be less than delta. So with x0 is equal to 1, x minus 1 is less than delta, then x is less than or should be less than delta plus 1. We replace x in f of x minus L in absolute value less than epsilon by delta plus 1. So 3 times x, which is delta plus 1, plus 2, this is f of x, minus L, which is 5, the limit is 5, remember, is less than epsilon. So 3 delta plus 3 plus 2 minus 5 is less than epsilon, 5 minus 5, 0, less than epsilon. So 3 delta is less than epsilon. And we need to choose delta equal epsilon divided by 3. Hence the limit is proven, because if we replace delta back in the function, you get the limit. And both, by the way, delta and epsilon are very small values. So this proves the limit exists. One-sided limits. Okay, what are one-sided limits? So we have at first right-hand limit. Right-hand limit is limit f of x as x approaches a plus, which is the right side of a. Like the zone to the right, immediately to the right of x equal a, is equal to L if the definition holds for x greater than a. Left-hand limit is the limit of the function at the left side of a, of x equal a. Just to the left, like immediately 1 iota to the left. So it is limit of f of x as x approaches a minus is equal to L if the definition holds for x less than a. For the limit to be two-sided and to exist at a, limit f of x as x approaching a minus should be equal to the limit as x approaches a plus is equal to the limit at a exactly of f of x equal L. In other words, the limit to the left at the point exactly and to the right of a should be equal, which means that the function has a limit at x equal a, and it is continuous between minus a minus and a plus. In other words, so the function has a limit, it has a value at x equal a, and that value is the same to the left of x equal a and to the right. Continuity at a point. Function f of x is continuous at a point x equal a if limit of f of x as x approaches a is equal to f of a. So the limit is actually the same as the value of f at x equal a. The limit of the function as x approaches a or tends to a is equal to the value of f of a, the value of the function at x equal a. Now, f of a should exist as a definitive value. So it should be defined. It should have a value. The limit exists at x approaching a at a. So limit f of x as x approaches a exists. And the equality, which means limit of f of x as x approaches a is equal to f of a. These are the three conditions of continuity. Continuity on an interval. A function is continuous on an open interval AB, which means that A and B are not included within the interval. It is an open one, an open interval, so A and B are excluded if it is continuous at every point inside that interval, which is between A and B without A and B. Now, a function is continuous on a closed interval AB, and you see the square brackets. This means that A and B are also included if, at first, it should be continuous on the open interval AB, plus more than that, limit of f of x as x approaches a plus, which means the right side of a is equal to f of a, and limit of f of x as x approaches b minus, or the left side of b, so to the right of a, like immediately to the right side of a, and immediately to the left side of b, the limits should exist. So limit f of x as x approaches b minus is equal to f of b. Okay, so in such case, if it meets these conditions, these criteria, then f of x is continuous on a closed interval AB. Discontinuity a function f of x is discontinuous at x equal a if it fails to meet any of the three conditions mentioned above, okay? Which means that it is defined, it should have limits on both a and b. Actually, yeah, if it's discontinuous at a specific point, let's say a, this means that the limit does not exist. There's no definition of a point, so f of a does not exist. And limit f of x as x approaches a is different than f of a. These are the three conditions of continuity. If they are violated, or even if one of them is not met, then the function is discontinuous at x equal a. Continuities and types of discontinuities. Let's talk about what types of discontinuities we have. At first, removable discontinuity. This occurs when you have the limit of f of x as x approaches a exists. However, f of a is either not defined, so you don't have a value for f when x is equal to a, or it is not equal to the limit. So it is defined, it has a value, but not equal to the limit. Okay, removable, what does it mean, removable? It means that it is fixable by redefining f of a. You mean it's like, we mean it can be removed from the function, okay, x equal a, or the value of f at x equal a can be fixed by being removed from the function, and it will work out fine. So we can redefine f of a equal limit of f of x as x approaches a, okay? It's basically like a puncture within a fabric, okay, that you can fix that puncture, that hole, by filling it with something else, and then you would have no holes, you would have no undefined values within the rest of this mattress or this fabric. As an example, you have f of x is equal to x squared minus 1 divided by x minus 1, and okay, x different than 1. Now, x should be different than 1. Why? Because otherwise, you won't have a defined value. If x is equal 1, you would get 0 divided by 0, which is not defined on the function. So the function is discontinuous at x equal 1. So x equal 1 is removable because other than x equal 1, all the values work out fine for the function, and it would be defined, and it would have values and everything. It would be continuous throughout R. Non-removable discontinuities. These are discontinuities that cannot be removed by redefining the function at that point. These are broken down into the following classifications, and we're going to see how they differ from a simply removable discontinuity. So the first category is jump discontinuity, which means that the left-hand limit and the right-hand limit exist but are not equal. So limit f of x as x approaches a minus, or x approaches a from the left, is different than limit f of x as x approaches a to the right of a, okay, to the right side of a, which is a plus. So from the left and from the right, the value of f of x as x, or for x equal to a, from the left is a different value than that from the right. This is what it means. So as an example for that, you have f of x is equal to 1 for x less than 0, and for 2 for x greater than or equal to 0. So the value has jumped from 1 up towards 2 from left for x less than 0, okay, between x less than 0 and x greater than or equal to 0. So from left of 0 to the right side of 0, the value has jumped from 1 up to 2. This is a jump discontinuity. So we have a drastic jump at x equals 0, a drastic transition, like a digital signal that transitions from 0 to 1 suddenly. This is what it means. The other category, which is the infinite discontinuity, or in other words, it is called essential discontinuity. This means that one or both one-sided limits blow up to infinity. So as an example, you have limit f of x as x approaches a minus from the left of a is equal to plus or minus infinity, or as x approaches to the right of a. Okay, so from the left of a you might have a value, but to the right of a, just to the right of a, the function jumps up to plus infinity or down to minus infinity. As an example for that, f of x is equal to 1 divided by x. This is discontinuous at x equals 0. Why? Because limit of x as x approaches 0 is equal to 1 divided by 0, which is plus minus infinity. Okay, so you have an explosion of the function blows up. This is how we label it, blows up to infinity, plus or minus infinity as x approaches 0, because we are dividing by 0. Hence, f of x is discontinuous at x equals 0. Oscillatory discontinuity. This is another interesting type of discontinuities, which means that the function oscillates infinitely near a point, but between two or different values. Okay, so it keeps jumping back and forth without ever settling over a fixed value. So basically, this means that the limit does not exist. As an example, f of x is equal to sine 1 divided by x. Now, at x equals 0, as x goes to 0, you have sine of 1 divided by 0, okay, which is sine infinity. Sine infinity means it is a sine signal, which is a harmonic signal that keeps oscillating, jumping back and forth between -1 and +1. Correct? Because these are the lower and upper boundaries for the sine function. But it never settles at a fixed value. So it keeps jumping back and forth near x equals 0. Exercise. Let f of x be equal to x squared minus 4 for x different than 2, and 1 if x equal 2. Check the continuity at x equal 2. If not continuous, check the type of discontinuities or discontinuity, because there's only one. You can pause the video, of course, try to solve it yourself first, then get back to the solution. Now, let's evaluate the limit at x equal 2. Limit f of x as x approaches 2 is equal to the limit of x squared minus 4 as x approaches 2 equal 0 or minus 4. But according to the proposition within the problem, for x equal to exactly, f of x is equal to 1, which is different than the limit. In other words, f of 2 is equal to 1. Meanwhile, the limit is equal to 0. So limit f of x as x approaches 2 is different than f of 2. Hence, the function is not continuous at x equal 2. The type is removable discontinuity. In other words, if we remove the value 1 at x equal 2, the function becomes continuous everywhere. Second exercise, f of x is equal to 1 divided by x minus 5. Is f of x continuous at x equal 5? And what is the type of discontinuity if not? Again, pause the video if you want to solve it first before getting back to the solution. So, let's examine the denominator. We have x minus 5 should be different than 0, correct? So let's solve x minus 5 is equal to 0. X equal 5 renders the denominator 0. So f of x is not defined at x equal 5. Why? Because we would be dividing by 0. And limit f of x as x approaches 5 is equal to 1 divided by 5 minus 5, which is 1 over 0. It approaches, actually it blows up to infinity. So the function blows up to infinity, x equal 5, and hence it's not defined at that point, nor it is continuous. This is an infinite or essential discontinuity. Also, on top of that, limit 1 divided by x minus 5 as x approaches 5 minus, or as x approaches the left of x equal 5 is equal to 1 divided by 5 minus minus 5. Okay, 5 minus means it is a value a little bit less than 5, which renders the entire fraction or the entire quotient negative. So it approaches minus infinity. Meanwhile, for x approaching 5 plus, okay, a value a little bit greater than 5 becomes 5 plus minus 5, which gives you a positive value right after 0. So 1 divided by 0 plus gives us plus infinity. The left side and the right side limits are not equal, so also at x equals 5, since they do not match, the function is not continuous. Exercise 3, f of x is equal to sine x, x different than 0, and 5 if x equals 0. Now, is f of x continuous at x equals 0? If not, find the type of discontinuity. Again, pause the video if you want to solve it before getting to the solution. So, let's evaluate the limit. Limit f of x as x approaches 0 is limit of sine x as x approaches 0, or sine 0, which is equal to 0. So, the value at x equals 0 equals 0. However, based on this criteria here, if x is equal to 0 on the limit, x equals 0, f of 0 is equal to 5. Okay? So, unlike the limit which gives you limit f of x as x approaches 0 equals 0, if x is equals 0 exactly, the value is 5 for the function. As the function is not continuous at x equals 0, and the discontinuity is removable. Why? Because it occurs at one specific point and it is removable. So the function is not continuous at x equals 0 again because it jumps from 0 to 5 at x equals 0 exactly. Meanwhile, as the limit approaches 0, the function is equal to 0, hence when it arrives to x equals 0, it jumps to 5. Properties of continuous functions. Okay, algebraic operations preserve continuity. In other words, if f of x and g of x are continuous at x equals a, then f of x plus g of x is continuous at a, f of x minus g of x is continuous at a. Also, the multiplication is also continuous at a. The division f of x divided by g of x is continuous, given that g of a should be different than 0. And c multiplied by f of x, where c is a constant in R, is also continuous. Composition of continuous functions. Let's say you have a function that is composite, which is g f of x, so function within a function, a nested function inside. It is continuous at x equals a. If f is continuous at x equals a, then g is also continuous at f of a. IVT, or Intermediate Value Theorem. Let f be a function that is continuous on a closed interval AB, a and b are included, and let n be any number between f of a and f of b. Then there exists at least one number c within a and b boundaries, okay, or open boundaries, such that f of c is equal to n. So f has a value, a defined and continuous value at x equals c, which is supposedly n. Okay? In other words, if a function is continuous, it takes every value between f of a and f of b if it is continuous within the closed interval a and b being defined. Now, what are the necessary conditions? F is continuous on the closed interval a and b. That's the first condition. So f has values on the interval a and b. It is continuous on the closed interval a and b. More than that, f of a should be different than f of b, and f of b should have different signs. So one should be negative and the other should be positive, which means that f has a value n, okay, between f of a and f of b, such that f of a, or n, is between f of a and f of b, okay, greater than f of a, less than f of b, or n is greater than f of b, less than f of a. This is what the notation means. Example, show that the equation f of x is equal to x3 plus x minus 1 equals 0 as a solution in the open interval 0, 1. You can pause the video, try to solve it before getting back the solution. Okay. So let's evaluate the limit at x or when x approaches 0, limit f of x as x approaches 0 is equal to the limit of x3 plus x minus 1 as x approaches 0 equal f of 0 equal minus 1, which is less than 0, by the way. Okay, so f of x is actually defined and has a limit and continuous at x equal 0. Then limit f of x as x approaches 1 is equal to the limit of x3 plus x minus 1 as x approaches 1 equal f of 1 equal 1 plus 1, which is greater than 0. Now this is remarkable since we have the function f of x is defined and continuous and has limits between 0 and 1, or at x equals 0, x equal 1. So more than that, f of 0 is negative, f of 1 is positive. So you have two different sides, which means there exists at least one value equals c for which f of c is defined. It has a value n. So f of x has a limit and is defined on both x equals 0, x equal 1. More than that, f of 0 is different than f of 1, and f of 0 is less than 0, f of 1 is greater than 0. So two opposite signs, which satisfies the condition for the function to be continuous, not only continuous on 0, 1, but also having a value c for which f of c is defined. So there definitely exists a value c within a b interval such that f of c exists and f is continuous at x equal c. Okay, show that the equation f of x equal cosine x minus x is continuous at 0, 1. Pause the video, try to solve it first. Okay, let's check the limit at x equals 0. Limit f of x as x approaches 0 is equal to f of 0 equal cosine 0 minus 0, which is 1 minus 0 or plus 1, greater than 0. So f of x has a limit, is defined, and is continuous, and also has a positive value at x equal 0. Checking the limit at x equal 1, limit f of x as x approaches plus 1 is equal to cosine 1 minus 1. Now, cosine 1 is slightly less than plus 1, so which is approximately equal to minus 0.0015, less than 0. So f of x has a limit, is defined, continuous, and is negative at x equal 1. First of all, the criteria have been met. So f of x is continuous at x equals 0 and x equal 1. f of 1 is different than f of 0, and both have opposite signs. So one is positive at x equals 0, the other one is negative at x equal 1. Hence, they satisfy the IVT criteria. So there can be found at least one value c for which f of c is equal to n, which is continuous and defined within the closed interval 0, 1. For which real value a does g of x equals 0 have a solution in the closed interval minus 1 plus 1? A little bit challenging exercise here. You have g of x is equal to e to the power of x minus ax. Okay, let's start with the conditions for the IVT or Intermediate Value Theorem conditions to be met. Okay, for g of x to have a value defined and continuous on the closed interval 0, 1, meeting the IVT criteria, limit f of x as x approaches minus 1 should exist, and so should the limit of f of x as x approaches plus 1. More than that, f minus 1 and f plus 1 should have different values and should also have opposite signs. Or in other words, what does it mean, opposite signs? So f of minus 1 and multiplied by f plus 1 should be less than or equal to 0. Actually, should be less than 0. So f minus 1 multiplied or times f plus 1 should be less than 0 for the condition of having opposite signs to be met analytically. So limit f of x as x approaches minus 1 is equal to f minus 1 equal e to the power of minus 1 plus a. Limit f of x as x approaches plus 1 is equal to f plus 1 equal e minus a. E minus a. You replace x by plus 1 in the second and by minus 1 in the first. The second criteria again is f of minus 1 multiplied by f of plus 1 should be less than 0. Or in other words, they need to have opposite sign. One is greater than 0, one is positive, the other one is negative. Okay, so f minus 1, which is e to the power of minus 1 plus a multiplied by f plus 1, which is e minus a, should be less than or equal to 0, actually preferably less than 0, of course. So e to the power of minus 1 is 1 over e multiplied by e minus a multiplied by e to the power of minus 1, which is minus a divided by e also, plus ae minus a squared, less than 0. Okay, which gives you e minus a plus ae squared minus a squared e less than or equal to 0, because the other side has been multiplied by e. Now, this is a polynomial form, by the way. When you reduce it to a squared e plus a multiplied by 1 minus e squared minus e is greater than or equal to 0. We flip the signs. This is what happened here, because you had here minus a squared e plus a multiplied by e squared minus 1. It's a common factor, plus e less than or equal to 0. We multiplied by minus, so we flip the sign at the end. This is of the form ax squared plus bx plus c equals to 0, which is a polynomial equation. Delta is equal to b squared minus 4ac. All right, so delta, the discriminant, we need the discriminant to find the roots of this equation, to find for what values of a we have critical points. We have, if you want, values for which this becomes 0. F of x multiplied by f of 1 multiplied by f of minus 1, to see or to observe for what values we have negative f of minus 1 multiplied by f plus 1. For which values of a we have opposite signs for f plus 1 and f minus 1. So delta is equal to b squared, which is 1 minus e squared minus 4ac. Minus 4 multiplied by e multiplied by the second e, which is minus e here, which is plus 4e squared, okay? Equal to e4 plus 2e squared plus 1, which is e squared plus 1 squared. Okay, so let's find the roots. x1, which is a1, in other words, is equal to minus b minus square delta divided by 2a. x2 equal minus b plus square delta divided by 2a. This is how we solve a polynomial equation. Okay, x1 here refers to the form, the original form of a polynomial equation. Also, x squared is actually in the original equation here a squared. Okay, you don't want to mix them up. Okay, and a here we're talking about is the argument multiplying x squared, which is e. It's not the actual a. All right, so x1 is equal to minus b minus 1 minus e squared minus square delta, which is e squared plus 1 squared, divided by minus square root of e squared plus 1 squared divided by 2e equal to minus 2e squared divided by 2e equal minus e. x2 equal minus b plus square root of delta divided by 2e, which is minus e squared minus 1 plus e squared plus 1 divided by 2e, or 2 divided by 2e, because e squared cancels out in such case, equal 1 over e. So this is the interval. A should be less than or equal to minus e and 1 over e. Okay, let's check the limit of g of x, or x approaching minus 1, when we use the first value, which is minus e. Instead of a, okay, we're going to replace a by minus e. So it is limit as x approaches minus 1, ex plus ex. First one is e to the power of x plus e multiplied by x equal g minus 1 of that value equal e minus 1 minus e, or 1 minus e squared divided by e, which is less than 0. Now, for x approaching plus 1, limit of g of x. Now, for x approaching plus 1, limit of g of x is equal to limit x approaching plus 1 of e of x plus ex equal to e plus e or 2e greater than 0. So we have two different values with two different signs, and the function is continuous at both x equal minus 1 and x equal plus 1. So g of x is defined and continuous on x equal minus 1 and x equal plus 1 for a equal minus e, and g minus 1 multiplied by g plus 1 is less than 0, which means it has different signs for minus 1 and plus 1. Therefore, there exists a value c for which f of c is equal to n is defined and continuous on the interval, closed interval, minus 1 plus 1. Okay, now for x equal 1 divided by e, the function has limits, but it produces two positive results for x equal 1 and x equal minus 1, which does not satisfy the IVT, the Intermediate Value Theorem criteria. Now, meanwhile, let's consider a equal minus 2e instead of minus e minus 2e, a lesser value than e, okay? So limit g of x as x approaches minus 1 is e to the power of minus 1 minus 2e equal 1 minus 2e squared divided by e less than 0. Limit g of x as x approaches plus 1 is equal to the limit of ex plus ex as x approaches plus 1 equal to g plus 1 e plus 2e equals 3e, which is greater than 0. So g of x is defined and continuous on x equal minus 1 and x equal plus 1 for a equal minus 2e, and g minus 1 multiplied by g plus 1 is less than 0, which means it has different signs for minus 1 and plus 1. Therefore, there exists a value c for which f of c is equal to n is defined and continuous on the interval minus 1 plus 1. Extreme Value Theorem, or EVT. Let f be a function that is continuous on a closed interval ab. Then there exist points c and d within the closed interval ab such that f of x is greater than or equal to f of c less than or equal to f of d. So f of x is between f of c and f of d, between two y values for all x within within the interval, the closed interval a b, or in other words, for all x between a and b. So f of x is always between f of c and f of d, okay, for all values of x, and when x is between a and b. Actually, it should be f of a less than or equal to f of x less than or equal to f of b for all values of x within the closed interval a and b. In other words, f attains a minimum at x equal c and a maximum at x equal d. This is what we're pointing at. Example, let f of x be equal to minus x squared plus 4x plus 1 defined on the closed interval 0, 5. Let's check the continuity at first and then find a maximum and a minimum. You can pause the video, try to solve it first before getting back to the solution. Okay, so let's check the continuity. Limit f of x as x approaches 0 equal f of 0 equal 1. So it is defined, it has a value, it has the limit, then it is continuous at x equals 0. And it's greater than 0, it has a positive sign. Now limit f of x as x approaches 5 is equal to f of 5, okay, because it's a polynomial, it's always defined on R. So it's equal to minus 25 plus 21 equal minus 4, and it is negative. So you notice, first, it satisfies the IVT, the Intermediate Value Theorem criteria, because it's continuous, defined, and f of 0, f of 5, both have different values, they have different signs. So there exists always a value c for which f of c is defined and continuous on this closed interval. So f of x is defined and continuous at x equals 0 and x equals 5, and it satisfies the IVT criteria. Now let's check if it satisfies the EVT criteria or the extreme value theorem, if it has a maximum and a minimum. In order to check whether a function has a maximum and a minimum, we should evaluate the derivative. Okay, we should differentiate the function to see if it's increasing or decreasing, and where does it have critical points. Critical points are the points where the function levels up. It becomes like the tangent against the function becomes parallel to the x-axis. So to find the maximum and minimum, we need to explore the derivative of the function, or the differentiation, to observe how the function is behaving, whether it's increasing or decreasing or both, and where. So f prime of x is equal to minus 2x plus 4. Let's find the roots for this function, which is, the values for which the derivative becomes 0. Derivative is the angle, is the slope of the tangent against the function. Okay, so where does the derivative become 0? It is at minus 2x equal minus 4. So at x equal 2, the derivative or the tangent to the function becomes parallel to the x-axis. So the function levels up at x equal 2. For x less than 2, the function hits the maximum. Okay, actually this is exactly at x equals 0. You hit the maximum. So max f is at x equals 0, which is equal to 1. Why? Because for x less than 2, the function is positive. It is increasing. Meanwhile, for x greater than 2, and we notice that through the derivative, the function is decreasing, becomes negative, because the derivative is negative, so it should hit a low, a minimum. And the minimum inside the interval, the closed interval 0, 5, is at x equals 5, which is f of 5 is equal to minus 4. So we have both maximum and minimum. All right, f of x is equal to x to the power of 3 minus 3x squared plus 4 on the interval 0, 3. Show that f attains both absolute maximum and absolute minimum on 0, 3 closed interval. And find the maximum and minimum and the points for which they occur. You can pause the video, try it yourself before getting back to the solution. Let's evaluate at first the derivative to get critical points, where the tangent, or critical points, is where the tangent against the curve is parallel to the x-axis, as we mentioned before. Now f is polynomial, hence it is continuous throughout R, throughout the real numbers interval, the real numbers scope or space. Let's get the derivative. So f prime of x is equal to 3x squared minus 6x. The roots for that function are, okay, x is a common factor, so x multiplied by 3x minus 6 is equal to 0. You have x equals 0, that's the first critical point, and 3x minus 6 equals 0, or 3x equals 6, so x equals 2, that's the second critical point. Now, for x between 0 and 2, f prime of x, okay, so if x is between the two roots that we found, the derivative has the opposite sign of a, which is, this is a, opposite sign of a, so it is negative. F prime is less than 0. Otherwise, f prime has the same sign of a, so it would be positive. Okay, so inside these boundaries, the function is decreasing. Outside, the function is increasing. This is what it means. So f of x decreases within the interval based on the derivative, and increases outside of the interval. So f of x reaches a peak twice, before 0 and after 2. Okay? And it reaches a trough, or a low bottom between 0 and 2. Let's check them out. So let's find the maximum and minimum. F of 0 is equal to 0, minus 3 times 0 plus 4 equal 4. That's first maximum. F of 2, okay, at x equal 2, it is 8 minus 12 plus 4 equals 0, that's minimum, and f of 3 equal 27 minus 27 plus 4, which is equal to 4. So the maximum, or 4, is hit twice at x equals 0 and x equals 3, and the minimum 0 is hit once at x equal 2. Show that xex equal 1 has a solution C within the boundary. Actually, not, it's an open interval, 0, 1, 0 and 1 not included. That's 1, and prove the solution is unique on 0, infinity. Then approximate C to 4 decimal places. Okay, f of x is equal to, by the way, this is another way to write this function. You write that f of x is equal to x times e to the power of x minus 1. Pause the video if you want to try to solve it before getting to the solution. All right. Now, let's check the limit. Limit f of x as x approaches 0 equal to f of 0 equal to minus 1, correct? You have 0 times e to the power of 0, 1. Yeah, but it is multiplied by 0 still. So it is minus 1 less than 0. The limit at x equals 0 exists. It is equal to f of x, so when the limit as x approaches a specific value of f of x. Okay, let's say limit f of x as x approaches a is equal to f of a. So the limit exists, the value is defined, the function is defined at that point. And since they are both equal each other, then the function is continuous at x equal 0. Limit f of x as x approaches 1 is equal to f of 1 equal to e minus 1. Okay, you simply replace x by 1, which is greater than 0, because e is approximately 2.72. It is Euler's number. So e minus 1, it is approximately 1.72, greater than 0. Hence, the limit at x equal 1 exists and is equal to f of 1. So the function is continuous at x equal 1. F of x is continuous so far at x equals 0, x equal 1. Moreover, f of 0 is less than 0, but f of 1 is greater than 0. So they are different, they have different values, and also they have opposite signs. One is positive, one is negative. So they meet the IVT criteria. They meet the Intermediate Value Theorem conditions. Therefore, there exists at least one number C for which f of c has a value and is continuous on the open interval 0, 1. Uniform continuity. Definition. A function f that is defined within A being a subset of R, is said to be uniformly continuous on a set A within R. It can be the entire real space or a part of it, okay, real number space. If for every epsilon greater than 0, there exists a delta greater than 0, such that for all xy within A, if x minus y is less than delta in absolute value, which means if the distance between x and y is less than a specific number delta, then f of x minus f of y in absolute value, or the distance between f of x and f of y is less than epsilon. So, in other words, to put it mildly, so to speak, the change between x and y being two values within R, should not be less rapid than the change between f of x and f of y. Or, the gap, the distance between f of x and f of y should not be larger than that between x and y. Now here we have unique cases, okay, special cases, so to speak. Let f of x, for example, equal x squared be on the defined on the interval 0, 2. F is continuous on a closed and bounded interval such as 0, 2. 0, 2 is closed and bounded. Okay, so if f is continuous on that closed and bounded interval, by the Heine-Cantor Theorem, this function would be continuous uniformly throughout that bounded interval. Since it is bounded on 0, 2, it is defined on 0 as a limit f of 0 equal limit of f of x as x approaches 0. Also, limit as x approaches 2 of f of x is equal to f of 2. So it is continuous both on 0 and 2, on the interval 0, 2, the closed bounded interval. Hence, it is uniformly continuous on that interval. Not uniformly continuous, so let f of x be equal to x squared on 0, infinity. Of course, 0, infinity are not included within the interval. Though f is continuous on 0, infinity, it is not uniformly continuous because as x approaches infinity, the slope of the graph increases, correct? So the slope of the graph increases drastically. So small changes in x, in other words, produce arbitrarily large changes in f of x because it is a squared value. That's why you cannot find a single delta value that works for all x in the domain such that as x changes, f of x changes in the same way, in the same speed. But instead, f of x is equal to x squared, you see the squared value, changes parabolically. Okay, not exponentially, parabolically, but it has a more rapid change than that of x. That's why it's not uniformly continuous on 0, infinity. Checking the uniform continuity. If the domain is closed and bounded, like we've seen previously on 0, 2, you have 0 and 2 closed and bounded. If the function is continuous on that interval, then it is uniformly continuous as well. Okay, this is called the Heine-Cantor Theorem. Now, again, this is a special case. Secondly, if the function grows rapidly or has vertical asymptotes, consider that it's definitely not uniformly continuous. Why? Because we have high jumps, sudden jumps, and drastic changes in the value of y as x changes gradually. So it's not uniformly continuous on such an interval. Like when you calculate the limit of 1 of x, as x approaches 0, it blows up to infinity. So it's not uniformly continuous on 0, neither on an interval that includes 0. Third, try to find a counterexample, which is by choosing sequences xn and yn, okay, such that xn minus yn, as it approaches 0, f of xn minus f of yn should also approach 0 for the function to be uniformly continuous. And again, as a reminder, a critical point of continuity, uniform continuity, for epsilon greater than 0 and delta greater than 0 exists two values, x and y, such as f of x minus f of y. The distance between them should not exceed epsilon, as x minus y remains bounded within delta. Lipschitz continuity. A function f defined on D, domain D within R, is Lipschitz continuous on D if there exists a constant L less than or equal to 0, such that for all xy that are represented on D, f of x minus f of y is less than or equal to L multiplied by absolute value of x minus y. L, by the way, would be the derivative of the function, okay, f prime of x, which is defined by f of x minus f of y divided by x minus y. L is called the Lipschitz constant. Every Lipschitz continuous function is uniformly continuous, but not every uniformly continuous function is Lipschitz. Lipschitz theorem in real analysis: if f is differentiable on a convex set D within R to the power of n, and its derivative is bounded, so D fx is within M for all x within D, then f is Lipschitz continuous with Lipschitz constant L is equal to n. Use the mean value theorem in vector form, so f of x minus f of y less than or equal to the supremum of D f of z multiplied by x minus y, and we will see examples afterwards. Exercise. Let f be defined on 0 infinity open bounded interval equal to sine x divided by x. First, prove that f is uniformly continuous at 1 infinity with a closed bound from one side. Determine that f is uniformly continuous on 0 infinity, the entire interval. And third is f continuous on 0, 1. So you can pause the video and try to think about it at first before getting back to the solution. Prove that f is uniformly continuous at 1 infinity, and 1 is the closed bound. Limit f of x as x approaches 1 is equal to f of 1 equals sine 1. So f of x is then defined and has a limit at x equal 1, and the limit is equal to f of 1, hence it is continuous at that point. Now let us differentiate the function to check how the function behaves. G of x is equal to f prime of x equal, okay, how to differentiate? Let's say the numerator is u and the denominator is v. It is u prime v minus u v prime divided by v squared. Prime means the derivative of u. So u prime, the derivative of u, v prime, the derivative of v, the denominator. So u prime v, which is cosine x times x, minus u v prime minus sine x divided by v squared, which is the denominator square. Lipschitz continuity is proven by the following premise. If f of x minus f of y is less than f prime of x multiplied by x minus y. Okay, now g of x is equal to f prime of x equal x times cosine x minus sine x divided by x squared, and the derivative should be less than or equal to 1. Okay, so it is x cosine x minus sine x divided by x squared. With cosine x and sine x, we already know that these two have an upper boundary plus 1. They cannot go beyond that. So f prime of x, an absolute value of course, is equal to absolute value of x cosine x plus absolute value of minus sine x divided by x squared equal x cosine x plus sine x divided by x squared. And you know that this is less than or equal to x plus 1 divided by x squared. Sine x and cosine x are less than or equal to 1. Their maximum is 1, which is less than or equal to x divided by x squared, which is 1 over x plus 1 over x squared. Now, at best, this would be less than or equal to 2, because for x equal 1, and you know that the lower boundary is 1, so you have 1 plus 1 is equal to, and as x increases, this decreases to 0. So fx minus f of y less than f prime of x multiplied by x minus y. So f of x minus f of y is less than epsilon x minus y less than delta. This is the rule to prove the uniform continuity. So you have f prime of x is 2, and you know that x minus y should be less than delta. Okay, so we consider it delta. So you have 2 times delta, and f of x minus f of y is epsilon. So epsilon should be less than 2 delta. Hence, delta is greater than epsilon divided by 2. So we choose delta equal epsilon over 2. The function f is Lipschitz continuous, as we choose this value, on 1 infinity. Hence, it is automatically also uniformly continuous. Second, determine that f is uniformly continuous on 0, infinity. Of course, 0 and infinity are excluded. Limit f of x as x approaches 0 plus. Let's check that limit. It is equal to limit x approaching 0 plus sine x divided by x, which is equal to 1. We know that for very small values, sine x approaches the value of x. So limit sine x divided by x as x approaches 0 plus is equal to 1. And by the way, sine x over x gives us cardinal sign. However, sine 0 divided by 0 is not defined. So we don't have the value, we have the limit, but sine 0 divided by 0 is undefined. But in all cases, the function remains close to 1. And we've already proven that f is uniformly continuous on 1 infinity. So it is also uniformly continuous on 0 infinity, because the limit is 1 and 0 is excluded. So it remains close to 1. Hence, it is uniformly continuous on 0 infinity, not only on 1 infinity. On the interval 0, 1, is it continuous? No. Both the numerator sine x and the denominator are continuous. And x is different than 0 for all x in this interval. So the quotient of continuous functions is continuous wherever the denominator is non-zero. Hence, f is continuous at every point of 0, 1. Again, a quotient of continuous functions is continuous wherever the denominator is non-zero. Since x doesn't actually go to 0, it approaches 0, and we've proven that limit of sine x divided by x as x approaches 0 is 1. Since sine x and x both are continuous, so the quotient is continuous at 0, or starting from 0 to the right, okay, all the way to 1. And we've proven that at 1 we also have a defined value and it is continuous at 1. So the function is uniformly continuous on the interval 0, 1. Let f of x be equal to 1 divided by x. Study the continuity at 0, infinity, unbounded. At 1, infinity, 1 is bounded. Infinity, of course, is always unbounded. An open interval to the right. At delta 1, which is a closed, bounded interval. Okay, given that delta is greater than 0. You can pause the video right now and try to solve it before coming back to the solution. Okay, at first, let us check the limit at x equals 0. So, limit f of x as x approaches 0 is equal to 1 divided by 0, which is infinity. X equals 0 is problematic because we cannot divide by 0 in the denominator, correct? So it is the value for which f of x blows up to infinity. Hence, f is not continuous at x equals 0. It goes haywire, so to speak. Like it jumps to an infinite value as x approaches 0. Because on one hand, it is undefined and the limit doesn't exist. There's an approaching limit, but not a definite value. Okay, it approaches infinity. Okay, let us check the derivative of f. So f prime of x is equal to u prime v minus u v prime divided by v squared, which is minus 1 divided by x squared. At x equals 0, f prime of x is not confined at a value. Okay, it goes up also to minus infinity. And hence, Lipschitz doesn't apply. So f of x is suspected to not be uniformly continuous at 0 infinity. Now, mind you that every Lipschitz continuous function is immediately considered as uniformly continuous. But the opposite is not necessarily always true. So let us prove it using the xy approach. Okay, so how to prove uniform continuity? Let epsilon be greater than 0, delta be greater than 0, and xy greater than 0. For x minus y, an absolute value less than delta, f of x minus f of y is less than epsilon. In other words, as x approaches y, okay, with a distance between them of delta, f of x minus f of y, the distance between fx and fy should be less than epsilon. Let's use the sequence method, adopting x of n equal 1 divided by n, y of n equal 1 divided by n plus 1. So xn minus yn would be equal to 1 divided by n minus 1 divided by n plus 1. So we consider both x and y as two sequences, okay, which is equal to n plus 1. Minus n divided by n times n plus 1. And this is definitely less than delta y because the limit of 1 divided by n times n plus 1 is equal to 0. Now, f of x minus f of y is equal to, you flip, it is 1 divided by xn minus 1 divided by yn, okay? Which is n, because you get the inverse, minus n plus 1, which is equal to minus 1 in absolute value, is plus 1. So for small changes of x that are close to 0, limit n approaching infinity of 1 divided by n times n plus 1 is 0. f of x doesn't approach 0 because we see that f of x minus f of y is equal to 1, which is not even close to 0. So f of x is not uniformly continuous on 0 infinity. Let's check right now at 1 infinity. First of all, limit of f of x as x approaches 1 is equal to f of 1 equal 1. So f of x has a limit, but not only that, it is defined on x equal 1. And the limit is equal to the value of the function at that point as well. Hence, it is continuous at that x equal 1. Now let's recall that f prime of x is equal to minus 1 divided by x squared. The derivative is defined for all values of x that are greater, strictly greater than 0. Now, on the other hand, limit of f prime of x in absolute value as x approaches infinity is equal to 0. So the maximum of the derivative is 1, which is, by the way, the slope of the tangent against the function. Okay, this is L. F prime of x is L in Lipschitz continuity, which is equal in this case to 1. So f of x minus f of y is less than or equal to 1 times x minus y. In other words, f of x changes in the same rhythm, okay, in the same speed as x and y change, okay? So x is changing, okay, between two values, f of x also is changing in the same speed, with the same rapidity, so to speak. This satisfies Lipschitz theorem, and since f of x is Lipschitz continuous at 1 infinity, of course, therefore it is uniformly continuous as well. Let's check the uniform continuity at closed interval, which is bounded also, by the way. Delta 1 with delta is strictly greater than 0. Let's check the limit as x approaches delta of f of x. Okay, so the limit of 1 over delta as x approaches delta is equal to f of delta equal 1 divided by delta. Since delta is greater than 0, hence f has a limit and a defined value at x equal delta, so f is continuous at x equal delta. Now, let's check for the second boundary, which is 1. Limit f of x as x approaches 1 is equal to limit of 1 divided by x as x approaches 1 equal f of 1 equal 1. So f is also defined and continuous on x equal 1. Now, since delta 1 is a closed and bounded interval on which f is continuous on both boundaries and within and for any value inside delta 1, hence it is uniformly continuous on that interval, which is called the Heine-Cantor Theorem. If a function is continuous and defined on a closed interval, it is uniformly continuous as well. Exercise. F of x is equal to square root of x. Is f uniformly continuous on 0 infinity? Infinity is open, of course. And on 0 infinity with 0 and infinity both unbounded. The first one, 0 is bounded, so 0 is included within the interval. You can pause the video if you want to solve it first. Okay, so f prime of x is equal to 1 divided by 2 square root of x. We are evaluating the derivative to see if we can prove it using the Lipschitz Continuity Theorem. So f prime of x is equal to u prime over 2 square root of u, with u being equal to x. It is the inside value of the square root. So f prime of x is equal to u prime, which is 1, divided by 2 square root of x, 2 square root of u. Now, f prime of x blows up for x equals 0, okay? It blows up to infinity, so it cannot be bounded. It doesn't have a finite value. Hence, okay, for x different than 0, the function can be defined, okay? Derivative can be defined. However, for x equals 0, the derivative blows up, okay, to infinity. So the function is not Lipschitz continuous, okay, because it doesn't have an upper bound m. Now let's check if it is uniformly continuous. Let epsilon be greater than 0, delta be greater than 0, xy greater than 0. For x minus y less than delta, f of x minus f of y, or the distance between fx and fy, should be less than epsilon. So checking uniform continuity, f of x minus f of y in absolute value is equal to square root of x minus square root of y. We can multiply that by the conjugate, both in the numerator and the denominator, which is a very perfectly crafted trick in order to solve that problem. So, square root of x minus square root of y multiplied by square root of x plus square root of y, both in the numerator and the denominator, equal an absolute value x minus y divided by square root of x plus square root of y. Okay, now let x be greater than y greater than 0, square root of x greater than square root of y. So you have, okay, square root of x plus square root of y greater than 0 and less than or equal to to square root of x, and square root of x is greater than square root of y. That's the reason. So now the denominator is never 0 in this case, okay? Because you either have x or y greater than 0. Again, okay, denominator is never 0. Let's check for the uniform continuity. So you have x minus y in absolute value divided by square root of x plus square root of y, with square root of x minus square root of y is definitely less than square root absolute value of x minus y. Okay? Hence, x minus y in absolute value divided by square root of x minus square root of y is definitely less than epsilon. Is definitely a lesser value than epsilon. Okay? Meanwhile, we know that x minus y in the first conditions should be less than delta. Okay? So, as x and y change, or their distance change within the delta gap, okay, the delta threshold, fx minus fy does not cross epsilon, okay? It's still limited to epsilon. Why? Because this is a very smaller value than delta, which is x minus y divided by square root of x minus square root of y. Therefore, f is uniformly continuous at 0, infinity with 0 included. Why? Given the fact that as x and y change, fx minus fy do not change much rapidly or much faster than that. We don't have an extreme jump or drastic variations in fx, fy. On 0, infinity, unbounded. So, f prime of x, going back to the derivative, is equal to 1 divided by 2 square root of x. Now, f prime of x is positive for all values of x greater than 0, which is the case here, because 0 is not included within this interval, okay? It is outside of the boundary. So, this tells us, by the way, the limit f prime of x as x approaches infinity is equal to 0. So, it is monotonically decreasing. F prime of x attains its maximum for x equal 1, okay, which is 1/2. As x increases, f prime of x keeps decreasing until it reaches 0. Hence, the maximum of f prime of x is at x equal 1, which is 1/2. Therefore, the function is Lipschitz continuous. Why? Because fx minus fy is less than or equal to 1/2 multiplied by x minus y, with f prime of x equal 1 is equal to 1/2, less than 1. So fx is Lipschitz continuous, hence it is automatically uniformly continuous as well. Note, Lipschitz continuous means that as x and y change slowly with a low gap, so does fx and fy in such way, okay, they change with a minor difference, minor distance or gap between them. So fx minus fy remains small, and there are no drastic sudden jumps. Exercise. Let f of x be equal to sine 1 divided by x. Is it continuous on R? X in the denominator of sine 1 divided by x is very problematic. Why? Because it cannot be 0. When you divide by 0, you get infinity. And limit f of x as x approaches 0 is equal to the limit of sine 1 divided by x as x approaches 0 equals sine infinity. And there's no limit in such case. Why? Because sine infinity is an oscillatory function. Okay? fx is oscillatory around 0, rapidly changing between -1 and +1. Hence, the limit does not exist at 0, and f of x is not continuous at that point. Okay? This is a harmonic discontinuity. This also means f of x is not uniformly continuous on R. Let's prove whether it's uniformly continuous using the xy greater than 0 method. We're going to use the sequence method xn, yn. xn is equal to 1 divided by n pi, and yn is equal to 1 divided by n pi plus pi over 2. Let epsilon be greater than 0, delta greater than 0. there exists xy greater than 0 such that fx minus fy, or distance between fx and fy, is less than epsilon for x minus y less than delta. Okay, we're going to assume xn is equal to 1 divided by n pi and yn equal 1 divided by n pi plus pi over 2. So we are solving the problem using the sequence method to prove whether it is uniformly discontinuous or not. Now xn minus yn is equal to 1 divided by n pi minus 1 divided by n pi plus pi over 2. Okay, we create a common denominator by multiplying n pi with n pi plus pi over 2. And in the numerator you have n pi plus pi over 2 minus n pi, okay? Equal pi over 2 divided by n pi multiplied by n pi plus pi over 2. As n approaches infinity, this entire quotient decays to 0. Okay, so limit as n approaches infinity of pi over 2 divided by n pi multiplied by n pi plus pi over 2 is equal to 0. Now, fxn minus fyn is equal to sine n pi minus sine n pi plus pi over 2. Why? Because sine 1 over x is equal to 1 over n pi, for x being xn, of course. Okay? For yn, the same thing, 1 over 1 divided by yn is equal to n pi plus pi over 2. Why? Because you need to flip or to reverse the numerator and the denominator. So we get sine n pi minus sine n pi plus pi over 2. We know that sine n pi plus pi over 2 is equal to cosine n pi. Okay, because sine alpha plus pi over 2 is equal to cosine alpha. Back to simple trigonometry rules. So it's equal to sine n pi minus cosine n pi. Sine n pi is always 0. Okay, so for all values of n, you have either sine 0 equals 0 or sine 3 pi, 4 pi, 1 pi is always 0 because the angle is 0. Same thing for cosine n pi. The angle is always a multiple of pi, okay, for whatever value of n we have. So it will oscillate between minus 1 and plus 1. Since we are getting the absolute value here, it's equal to plus 1, which doesn't approach 0. So when x minus y approaches 0, fx minus fy approaches 1. We are not having a variation that is symmetric between x and y and fx and fy. Okay? So it approaches 1 and not 0. So the gap is relatively large between fx and fy. Hence, f is not uniformly continuous on R. fx is equal to x2 for x less than or equal to 1 and 2x minus 1 for x greater than 1. Is f uniformly continuous on 0 too? You can pause the video, try to solve it first before getting back to the solution. Alright, now let's check the limit at x approaching 1 minus, meaning the left side of 1, okay? Because the problematic value, if you will, for x is 1. We need to test 1 to the left and 1 to the right to check the limit and to see if f is continuous at 1, okay, before checking it is continuous at 0 and 2. So let's check the limit at x approaching 1 minus from the left. It is equal to limit, okay, 1 minus means x is less than 1, so fx is equal to x squared. So limit x squared as x approaches 1 minus is equal to plus 1. Now checking the limit at x approaching 1, so x less than or equal to 1, it is the limit of x squared as x approaches 1 equal plus 1. Now checking the limit to the right, which is x approaching 1 plus, it is limit of 2x minus 1 as x approaches 1 plus is equal to 1. 2 times 1 minus 1. And we need to check the second equation. Why? Because the second equation conforms with the condition of 1 plus, which is x being greater than 1. So it is equal to 1. Now, limit fx as x approaches 1 minus is equal to limit fx as x approaches 1 plus to the right of 1 is equal to limit fx as x approaches 1 equal 1. Why? Because x approaches 1 means x equal to 1 strictly. So it is limit of x squared as x approaches 1 equal 1. Hence, f is defined and continuous at x equal 1. Now, for x approaching 0, the limit of f of x is equal to 0 being less than 1. Limit of x squared as x approaches 0 equals 0, so which is, by the way, equal also to f of 0. The limit exists and is equal to f of 0, and the function is continuous at 0. Now, limit f of x as x approaches 2 is equal to the limit, okay, x approaching 2 is greater than 1. So it is the limit of 2x minus 1 as x approaches 2 equal to 4 minus 1 equal 3. So the function is defined and continuous at x equal 2. So the limit of f exists for x equals 0 and x equal 2, and f is continuous at these 2 points. Limit f of x as x approaches 0 equal f of 0. Limit f of x as x approaches 2 equal f of 2. And since f is continuous on a bounded and closed interval, 0, 2, therefore, according to Heine-Cantor Theorem, it is uniformly continuous on that interval. fx is equal to x divided by square root of 1 plus x squared. Is f of x continuous on R? The denominator here is never 0 and always positive. Let's differentiate the function. So f prime of x is equal to u prime v minus uv prime divided by v squared. As a reminder, how to differentiate the quotient, we have u divided by v prime is equal to u prime v, derivative of numerator times v, minus u v prime, minus u times derivative of v, divided by v squared. Square root of u prime, so derivative of the square root of u is equal to u prime divided by 2 square root of u, with u being the inside part of the square root. So f prime of x is equal to u prime v, 1 times square root of 1 plus x squared, minus u v prime, derivative of square root of 1 plus x squared is 2x divided by 2 square root of 1 plus x squared, divided by square root of 1 plus x squared squared, equal 1 plus x2 minus x2 divided by 1 plus x squared times square root of 1 plus x squared. The maximum that this value can get is 1, given the fact that as x approaches infinity, this entire quotient approaches 0. Limit f prime of x as x approaches infinity equal 1 divided by infinity equals 0. So the maximum value is at x equals 0, okay, which is 1. So f prime of x is less than or equal to 1. Therefore, fx minus fy is less than or equal to f prime of x multiplied by x minus y. So L is equal to f prime of x equal 1. F prime of x in absolute value is equal to fx minus fy over x minus y less than or equal to 1. So 1 is the maximum. Therefore, the function is Lipschitz continuous. The function changes slowly and gradually for slow changes of x, in other words. And since this function is Lipschitz, then it is uniformly continuous as well. Let's check the limit at x equals 0. Limit fx as x approaches 0 is equal to ln 0 equal minus infinity. So the function blows up to infinity, minus infinity to be more accurate, at x equals 0. Hence, it is not defined, neither it is continuous at that point. Now let's use the xy method to prove it. Let epsilon be greater than 0, delta greater than 0. There exists xy greater than 0 such that fx minus fy is less than epsilon for x minus y less than delta. So fx minus fy equal ln x minus ln y, which is ln x divided by y. X minus y less than delta. Okay, now y is problematic. This can still be less than delta if y is equal to 0. So fx minus fy does not approach 0 when x, or for all values of x minus y, approaching delta. Why? Because if y is equal to 0, ln x divided by y is ln infinity, which blows up to infinity. We have a drastic curve in such case, a drastic variation. Therefore, Okay, since y is problematic in the denominator, because as it approaches 0, ln x over y blows up to infinity. So the function is not uniformly continuous on R, given that it is not continuous on 0. fx equal e to the power of x. Fx continuous on R? Let epsilon be greater than 0, delta greater than 0. There exists xy greater than 0 such that fx minus fy is less than epsilon for x minus y less than delta. We adopt the following sequences: xn equal ln n and yn equal ln of n plus 1. X minus y at first is equal to ln of n minus ln n plus 1 equal ln of n divided by n plus 1. Let's evaluate the limit as n approaches infinity, and we will use the L'Hopital rule. So it is limit of ln, we divide both numerator and denominator by n, which is the highest, or the variable with the highest power. So limit ln 1 divided by 1 plus 1 over n as n approaches infinity. This becomes 0, and we end up with ln1, which is also 0. Now fx minus fy is equal to e to the power of xn minus e to the power of yn equal e ln n minus e ln n plus 1. Now e ln a is equal to a, as we already know, equal to n minus 1, an absolute value which is equal to 1. So the uniform continuity holds, and analytically it means is the same way x minus y is close to 1, so does remain fx minus fy. In other words, it changes in the same speed. Another one, fx is equal to x sine 1 over x for x different than 0, and 0 for x equal to 0. Is fx continuous on R? Now, let's check the limit of f of x as x approaches 0 minus, which is 0 to the left, and for which x would be different than 0 still. So it is limit of x sine 1 over x as x approaches 0 minus equals 0, because we are multiplying by 0. So despite the fact that sine 1 over x keeps oscillating between minus 1 and plus 1, it is multiplied by 0, and so it goes to 0. Limit f of x as x approaches 0 plus is equal to the limit x sine 1 over x as x approaches 0 plus equals 0. Same thing as x approaches the right side of 0. So, and for x equals 0, f of x is equal to 0. We already know that. Hence, limit f of x as x approaches 0 minus, which is to the left, equal limit f of x as x approaches 0 plus to the right, equal f of 0 equals 0. So f of x is uniformly continuous on x equals 0 and for all values in R. Thank you so much for watching, and see you next time.